there are three equations that can be used to calculate energy changes. We've looked at them in reference to a phase graph, but often I hear the concern that people just don't know which equation to use. The equations themselves are easy to use, they just don't always know which one to use for a particular situation. If you look at your scenario and it involves a change in temperature, in some form you're using this equation: mass times temperature change times specific heat. It is the only equation that involves temperature. And to be more specific, delta T, change in temperature, is temperature final minus temperature initial. So if I look at number 1, we want to know how many joules of heat are needed to raise the temperature of 23.5 grams of methane from 18 to 45 degrees Celsius. I see temperatures, I see degrees Celsius, so this is my equation. I'm solving for amount of joules, that's like my delta H, change in heat, mass, 23.5 grams. Technically, temperature change is final, 45, minus initial, 18 degrees Celsius. And specific heat is a constant. You look it up on a chart. And I will give you all of these equations and these constants when you take the test. So this is methane, specific heat. There we are, 2.2. 2.2. And the unit is kind of important. Joules per gram, degrees Celsius. All of the other units need to match the units of the specific heat value. So my delta H is going to come out in joules, my mass needs to be in grams, and my temperature change needs to be in degrees Celsius. Sometimes they might try to trick you and maybe they'll give you mass in grams or kilograms or milligrams. If it's not in grams, I'm going to need to change it before I plug it into this equation. But there, that's it. So I have a temperature change of 27 degrees Celsius. We'll plug this all in and say delta H equals. Now I'm not going to pick too much on sig figs. I mean, I don't know, maybe we'd be looking at 2 or 3 significant figures. In my calculator I get 1,396 joules. And if you wanted to maybe go 2 sig figs, you could do 1,400 joules. I'm not going to be super picky on the significant figures, as long as you're within reason. All right, there, that's it, you're done. That didn't hurt so bad, right? Let's try another one. What is the energy change when 5 grams of water cool from 25 degrees Celsius, 75 degrees Celsius, down to 25 degrees? Okay, I see temperatures. So here we go. Let's plug in the variables. Delta H equals mass, 5 grams. Temperature change is final minus initial. So technically, this is 25 degrees minus 75. That's going to give me a temperature change of negative 50 degrees Celsius. That's okay. It's okay if you have a negative temperature change. It just means that your temperature is going down by 50 degrees. And that's exactly what's happening if we cool the water. And then finally, we need the specific heat. We look it up on a chart. We kind of mentioned that water is a little unique and that it has different specific heat values depending on the phase. So then we just need to look at the temperature range. So between 25 and 75 degrees, the water is a liquid. So we'll use 4.18 joules per gram degrees Celsius. Now because of that negative temperature change, my delta H value is going to be negative. Maybe like 1,045 joules. Negative. That's okay. When we look at our delta H value, in general, a positive delta H means that the change is endothermic. Well, yeah, we're raising the temperature of the methane, so we'd have to add heat. That makes sense. But in the second one, we are cooling the water. So anytime you are cooling a sample, we need to remove energy. So yeah, it makes sense that I have a negative delta H. It just means that the change is exothermic. And yeah, that makes sense. If I'm cooling something, I'm removing heat. So leave the negative in there. It's very important. It shows us the direction of the energy flow. I like those. Those are good. Now, you can use this equation and solve for any variable. As long as you have 3 of the 4, you can solve for the missing link. So, for example, if we knew the change in heat, which would be the joules, when 2.20 times 10 to the 4th joules of heat are added to a sample of water, the temperature changes from 34 to 100 degrees Celsius. What is the mass? All right, well, we're looking for mass. Let's leave that as our variable. Temperature change, final, minus initial, 34. Excellent. Then specific heat. Again, I have to know that within this temperature range, the water is most likely in the liquid phase. I'm assuming that we're not boiling it at 100. And so we would use the 4.18 joules per gram degree Celsius. Now all we have to do is a little algebra. Well, I can handle that. So let's see here. We're going to divide by our temperature change. We'll divide by our specific heat. My mass would be 79.7 grams. Since the specific heat value was in grams, my mass will come out in units of grams, and we do need to put the unit in there. And that's not bad, huh? Just a little algebra. Okay, so let's solve for the other 2 variables. We'll get 1 of each. Number 4, we're going to do this in the lab. What is the specific heat of copper if 23.5 joules of energy are required to raise the temperature of 1.85 grams of copper from 4 degrees to 37 degrees? Specific heat is a property that can be used to identify an unknown. So if I know the specific heat, I could look up the metal on a chart and I could kind of match an unknown metal based on that specific heat value. Well, this one they tell us it's copper, but I guess copper's not on the chart, so we could calculate its specific heat value. Let's see, the joules, 23.5 joules. That's my delta H, equals mass, 1.85 grams, times temperature change, final, 37 minus 4 degrees, initial, and then we'll leave specific heat as our variable. So again, it's just a little algebra. I can do this. 23.5 divided by 1.85 divided by my 33 degree temperature change. Specific heat is about 0.385. And the unit is joules per gram degrees Celsius. That's exactly what I did in my calculation. I took my joules, I divided by the mass, divided by the temperature change, algebraically to solve for specific heat. And so the units then on your specific heat kind of match. These aren't bad, huh? It's a nice change of pace from all that stoichiometry. And finally, we can solve for temperature. Predict the final temperature if 500 joules of energy, okay, that's my delta H, 500 joules, are absorbed by, here comes my mass, 20.7 grams of iron if the initial temperature is 15 degrees Celsius. Okay, so we're eventually looking for the final temperature. I might actually leave delta T, change in temperature, as my variable. And then as long as I know that it's iron, I can go back and look up its specific heat. Iron, there you are, 0.449. So we've got 0.449 joules per gram degrees Celsius. Now if I plug all this in, I'll solve for delta T, and I might be looking at around, with reasonable significant figures, 53.8 degrees Celsius. Now if they just asked you for temperature change, we'd be done. If they want you to predict the final temperature, you have a couple options. Now one option is to use that equation. Temperature change, I'll go delta T, equals temperature final minus temperature initial. And so we could plug in our variables. I know the temperature change, 53.8 degrees. I'm looking for the final temperature, and they do tell me the initial. Initially, we're at 15 degrees, so I could plug that in for my initial temperature. And then I could add on both sides and see that the final temperature is 68.8 degrees Celsius. There we go, done. Now your other option is to use your noggin. This is 500 joules of energy absorbed by my sample. If the energy is being absorbed, the temperature should increase. So if the temperature change is 53.8 degrees, we should go up by 53.8 degrees. If they said that it was 500 joules of energy released, then my temperature should go down by 53.8 degrees. So this is a pretty harmless little equation, right? You could use it to solve for any variable. It's plug and chug. You do a little algebra, that's not so bad. But the key is you can use this equation anytime the temperature is changing.